Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video we're going to review the substituent effects on electrophilic aromatic substitution reactions. In other words, we're going to talk about activators, deactivators, and OP versus metadirectors. Now, before you watch this video, it is crucial that you understand how the electrophilic aromatic substitution, or EAS, mechanism works. So if you don't understand that in its entirety, please go ahead and watch the video that I have on the EAS mechanism. On this slide, I have a summary of the four main types of substituents you can have attached to a benzene ring, as well as what they do and why they do it. You can come back to this at any time, but what we're going to do now is we're going to go over each of these different substituents in a lot more detail. The first substituent we're going to look at is something you should already be very familiar with, and that is an R group or an alkyl group, or a chain of carbons and hydrogens. In particular, an R group in this case is any group where a carbon is directly bonded to the benzene ring, provided that the carbon is not bonded to anything more electronegative than itself. In other words, we don't want that R group to have a partial positive or a positive charge. R groups are weak activators, and they're activating on the ring because, as we know about benzene, a benzene ring is nucleophilic because of all the pi bonds. R groups, as we've learned many times throughout organic chemistry, are electron donating due to hyperconjugation. In other words, they're going to add electron density to that ring, making it even more nucleophilic. R groups are also considered ortho-para directors. To understand why, let's take a look at the sigma complex formed in the following reaction. We're starting with toluene, or a benzene ring with a methyl group attached to it. And we're going to do an EAS reaction with Br2 and FeBr3 to add a bromine to the ring. Let's start with the ortho attack as shown here. The bromine is going to be added directly adjacent to that methyl group. The resonance structures for the sigma complex intermediate are shown here. Without the substituent, all of the resonance structures would be placed on secondary allelic carbons. But you can see here that with the very first resonance structure shown, that we have a tertiary allelic carbocation. That's going to make this intermediate more stable than if the group were not there, which means that we are lowering the overall activation energy of this reaction when we attack ortho. If we were to attack from the meta position, we're not going to get that stabilization on the sigma complex. You can see here that the carbocation never gets placed onto that tertiary allelic position, and all of the carbocations in the sigma complex are secondary. So there is no lowering of the activation energy when we attack from the meta position. What about the para position? Well, you can see here that when the bromine is added para to that methyl group, we do get a carbocation in the sigma complex that is at that tertiary position. That's why we say that R groups are ortho-para directors. The next substituent of interest is the Z group, and a Z group is simply an oxygen or a nitrogen with at least one lone pair. When we talk about Z groups, we say that they are strong activators and also OP directors, but these require a little bit more analysis than the simple R group. Z groups are more electronegative than carbon, so they do withdraw electron density from benzene rings via induction. However, we say that they're strong activators, not deactivators, so why is that? Nitrogen and oxygen can be considered to be strong bases, and as strong bases, they can readily donate their electrons to the benzene ring via resonance. And as it turns out, the resonance effect strongly outweighs the inductive effect of the Z group, making the ring more nucleophilic. Now, when it comes to the directing effects of the Z group, we're once again going to take a look at the sigma complex for an explanation. We're going to start out again with an ortho attack, but this time we have a Z group on the ring. We have that OCH3. And with that ortho attack, what you'll notice is that we get one additional resonance structure that we didn't get when we had the R group. And that's because the oxygen has lone pairs, and we can form an oxygen-carbon double bond when we place that carbocation in a position adjacent to the oxygen. When we do a meta-attack, you can see that we never put that carbocation adjacent to the oxygen, which means that we are lowering the overall activation energy of this reaction when we attack from the meta position. When we do a meta attack, you can see that we never put that carbocation adjacent to the oxygen, which means that we are lowering the overall activation energy of this reaction when we attack from the meta position. so we never get that additional resonance structure. With the para attack, we also get that carbocation adjacent to the oxygen, so once again we will get an additional resonance structure. Because we get the additional resonance structures when we attack ortho or para, we're going to lower the overall energy of the sigma complex intermediate, therefore lowering the activation energy required for an ortho or para attack in an EAS reaction. The next substituent we're going to look at is the X group. And X groups are the halogens chlorine, bromine, or iodine. X groups are considered to be weak deactivators. In other words, their net effect on the ring is that they withdraw electron density, making it less nucleophilic. However, they're still ortho-para directors. Let's talk about why. Just like with the Z groups, the X groups are more electronegative than carbon, so they're going to withdraw electron density from the benzene rings via induction. However, unlike the Z groups, the X groups are only weak bases. So while they can donate electrons a little bit due to resonance, they do so to a much lesser extent. And as it turns out, the inductive effects slightly outweigh the resonance effects for X groups, making the ring a little bit less nucleophilic. That's why we say that they're weak deactivators. Despite X groups being weak deactivators, they're still ortho-para directors. This can easily be explained by once again looking at the sigma complex obtained from ortho and para attack versus the meta attack. Just like with the Z groups, we get an additional resonance structure when we attack from the ortho position or the para position that we do not get when we attack from the meta position. Therefore, we still lower the activation energy required for an ortho attack or a para attack relative to the meta attack. The final substituent is the Y plus group. A Y plus group is any group where the atom directly bonded to the benzene ring is partially positive or positively charged. The Y plus group is a strong deactivator, and it's the only group of the four that's a meta-director. Let's discuss why. Because of the partial positive or positive charge, the Y plus group will have a strong electron withdrawing effect on the electrons in the benzene ring via induction. In addition, if we actually have a positive charge on the Y plus group, then we will have resonance structures that pull electron density away from the ring, as shown here. You can see that we actually place the positive charge on the benzene ring via those resonance structures. These effects reinforce each other, making the ring significantly less nucleophilic. In other words, Y plus groups are strong deactivators due to the compounding effects of both induction and resonance. To determine why Y plus groups are meta-directors, we're once again going to look at the sigma complex formed via ortho attack, meta attack, and para attack. Let's start with ortho. We can see here that we have the NO2 group, a Y plus group, on the benzene ring. And once again, we are going to do an ortho attack with Br2 and FeBr3. You can see in that very first resonance structure drawn in the sigma complex that we put a positive charge directly adjacent to that positively charged nitrogen. Two positive charges next to each other is highly destabilizing. That's going to raise the activation energy for an ortho attack. If we were to do a meta attack, you can see that the carbocation in all three of the resonance structures is never placed adjacent to that positively charged nitrogen. Therefore, the activation energy won't be increased the same amount that it would have been for an ortho attack. Finally, if we look at the para attack, just like the ortho attack, we will get one of the resonance structures in the sigma complex that has the carbocation directly adjacent to that positively charged nitrogen, once again destabilizing the sigma complex intermediate from a para attack. In other words, we don't actually make the meta position more favorable, we just make the ortho and para positions less favorable because we raise their activation energies. That's why the Y plus group is a meta-director. Once again, I'm going to return you to this summary slide, so that way you can see all of the substituent effects, what they are and what they do, all in one place. If you'd like a downloadable copy of this, simply check out the notes for this video, where I'll direct you to how you can download this slide. If you found this video helpful, please drop me a like or leave a comment, and as always, please subscribe to my channel.